This is an example for calculating the eigenvalues and eigenvectors of a 2 by 2 matrix. Here's the matrix with numbers, 4 numbers, 2 by 2 matrix. Eigenvalues are obtained from the determinant of A minus lambda I. And what you have to remember is that the way you form this A minus lambda I matrix is that you take the A matrix and you subtract from the diagonals lambda. Then to expand the determinant, we do what we did before. So you have to cross multiply the diagonal entries, 34 minus lambda times minus 36 minus lambda. You have to be careful with several terms and the negative signs. So you use the parentheses wisely. Then you have to subtract from this product the off-diagonal entries product, minus 14 times 84. Then, of course, what you have to do is you have to expand this product and collect like terms and do some simplification. You get a second order polynomial. In this case, lambda squared plus 2 lambda minus 48. This is called the characteristic polynomial of A. And then the characteristic equation of matrix A is when you set this polynomial equal to 0. And then you have to solve this for lambda, which means that in general we will have 2 lambda solutions, and that means we have 2 eigenvalues in general for a 2 by 2 matrix. Most of the examples in web work can be factored out unless you have complex eigenvalues. So in this case we obtain the eigenvalues lambda equals minus 8 and lambda equals plus 6. Once you have the eigenvalues, we have to continue and find the corresponding eigenvectors. These eigenvectors have to be found separately for the 2 eigenvalues. So first, let's start with eigenvalue minus 8 and find the corresponding eigenvector. So if we take this equation A minus lambda I times V vector written as a 2-component V1 and V2, and we substitute now the eigenvalue lambda equals minus 8. So this matrix A minus lambda I will have this form where you subtract the eigenvalues, the now known eigenvalue minus 8 from the diagonal entries. Then you get this simplified matrix times the vector v1, v2 equals 0, and this is the same as writing the 2 equations for the 2 unknowns separately. It's very important to know that when we work with eigenvectors, when we try to find the eigenvectors, it turns out that only one of the 2 equations can be used. The other is a multiple of the first. So in this case, what you can see is that the second one is a multiple of the twice the first. So the second one is useless, basically. And when you try to solve the first one alone, that means that all you can do is express one variable in terms of the other. In general, it doesn't matter which variable you choose to express in terms of the other. I usually try to avoid fractions, so I use the variable with the smaller coefficient. In this case, we have v2 equals 3v1. But this doesn't say what exactly the values are. Now, at this point, we choose a value for one of the components. In this case, v1, I choose the value 1, which is very simple, nice integer. And after that, we get v2, 3. So that means that an eigenvector corresponding to eigenvalue lambda equals minus 8 is the vector 1, 3. And actually, all other eigenvectors are just multiples of this vector. After this, we continue with the eigenvector corresponding to eigenvalue lambda equals 6. The procedure is the same as before. We take this equation A minus lambda I times V1, V2 equals 0. We substitute the known eigenvalue. We subtract it from the diagonal entries of A. We obtain a constant matrix times this unknown vector V1, V2. And we can write it as a regular linear system of two equations. Again, only one equation is needed. It's up to you which one you choose. I choose usually the first one. And we get V2 equals 2V1. Again, we choose a nice value, V1 equals 1, and that results in V2 equals 2. And that says that an eigenvector corresponding to eigenvalue lambda equals 6 is the vector 1, 2. So we have now two eigenvalues, and each of them has an eigenvector corresponding to it.